There is a rock at the bottom of the Pacific Ocean that has been writing down the history of the galaxy. It did not mean to. It simply sat there, in the cold and the dark, more than 1,000 meters beneath the surface, and grew. A ferromanganese crust grows about as fast as a human fingernail grows in 1,000 years. Layer by microscopic layer, over millions of years, it pulled metal out of the seawater around it and locked it in place. Nothing on its surface moves. No light reaches it. The temperature barely changes from one millennium to the next. And buried inside those slow black layers, mixed in among something on the order of 10 sextillion ordinary atoms, were a few atoms that did not come from this world at all. They came from the death of stars. Tonight, a team of physicists has finished reading them, and what that rock recorded is older than the dinosaurs, older than the ocean basin the rock now sits in, and in one specific way, older than almost anything that human instruments have ever managed to date. Sit with the scale of that for a moment, because the rest of tonight depends on it. The sample is a slab of dark, dense mineral, the kind of unglamorous lump that has been dredged up from the deep ocean floor for over a century and mostly ignored. It is not a meteorite. It is not a moon rock. It is a piece of the Earth's own seabed, but it has one quality that makes it priceless. It grows so slowly, and it preserves what falls into it so faithfully that a single centimeter of it can hold 10 million years of history in clean, readable order. Run a probe down through it, and you are running a probe back through deep time, past the last ice ages, past the rise of the first humans, past the age when the continents sat in different places and the crust holds the line the entire way down. It is one of the most patient archives on the planet, and the people who study it have learned to ask it a very particular question, not what was happening on Earth, what was happening in the sky above it. The work was published on the 15th of June in the journal Nature Astronomy by an international team led out of the Helmholtz Center in Dresden, Germany, working alongside two of the most sensitive atom-counting facilities anywhere on Earth, both of them in Australia, one in Canberra and one in Sydney. They went looking for 3 radioactive isotopes that have no business existing on a planet as old and as settled as ours. Each of the 3 is a kind of cosmic fingerprint. Each one is made only in the most extreme events the universe produces, and each one decays away over time, so that any trace still present had to arrive relatively recently. In cosmic terms, from somewhere beyond the solar system, they found 2 of the 3. The absence of the third is the part that matters most, and it is the part we will build toward, because that absence is what allowed the team to put an actual date on the last event of its kind near us. Hold that idea, a missing element, and the date it reveals. What the 3 isotopes together describe is the last time the space around our solar system was lit by a specific kind of catastrophe. Not an ordinary exploding star, something rarer than that, and far more violent, the kind of event that forges the heaviest matter in existence, the gold in a wedding ring, the platinum in a catalytic converter, the silver in an old coin, the uranium and thorium that, decaying slowly inside the Earth, keep the core of this planet warm enough to drive the plate tectonics under our feet. None of it was made here. The Earth cannot make these elements, and the Sun cannot make them either. All of it was made out there, in events so rare that, in the entire neighborhood of our solar system, across the whole long life of the Earth, they have happened only a small number of times. Tonight's report is the measurement of when the most recent one occurred. So here is what we are going to do. We are going to walk through exactly what was found in that crust, and what each of the 3 isotopes is telling us, one at a time, in plain terms. We are going to explain how a team can count individual atoms of an element when a single atom of it is hiding among 10 sextillion others, and why that kind of precision was simply not possible until very recently. We will name the agencies and the facilities, the heavy ion accelerator in Canberra, the rare isotope facility in Sydney, the laboratory in Dresden, and we will explain why their data is trusted, how the measurements are cross-checked, and how the team ruled out the more ordinary explanations one by one before they accepted the extraordinary one. We will set out the timeline the data implies, and we will be careful throughout to separate what was measured from what was inferred. We will then place this finding inside the longer record, the roughly 30 years of patient work that built toward it. There is a clear historical pattern here, a chain of discoveries running from the first faint detection in the late 1990s through to a single landmark night in 2017. when an event in the sky finally showed scientists directly where the heaviest elements are actually born. That chain is its own story, with its own names and dates and numbers, and it deserves to be told properly. We will tell it. There is a personal dimension to this that is easy to miss and worth saying once at the start. The heaviest elements are not only in the ground and in the ocean, they are in the body of every person listening. The iron that carries oxygen through the blood was forged in ordinary stars. But a small set of heavier elements, the iodine the thyroid depends on, the molybdenum that certain enzymes cannot work without, the trace metals woven through the machinery of a living cell, trace back to the rarer process tonight's report is about. Every atom of that material was made in a stellar event that ended long before the sun existed, drifted through space for an unmeasurable stretch of time, and was eventually swept up into the cloud that became our solar system. The crust in the Pacific is not telling us about something distant and unrelated to us. It is telling us about the origin of part of what we are. That is the quiet weight under the numbers, and we will keep it in view. And then we will do the thing this channel exists to do. We will set the modern data down beside the older record. Because long before anyone could count an atom, long before anyone could have known that gold is forged in the collision of dead stars, people across the world reached for the same idea independently, in languages that never met, on continents that had no contact with one another. They decided that the precious metals were not truly of the earth. They decided that gold was the substance of the sky, the flesh of the sun, the sweat of a god, the bright leavings of something that had broken open in the heavens. They had no accelerators and no spectrometers. They were not measuring isotope ratios. But the conclusion they arrived at, stated in their own vocabulary, sits remarkably close to the one the instruments confirmed this month. There is a specific question in how they got there, and we will spend real time inside it before the night is done. Before we go further, a word about what this channel is. For anyone arriving here for the first time, we are the Last Light Bureau. Every night we take one real event from the official record, something confirmed by an agency, a telescope, a laboratory, or a monitoring network, and we report it plainly and carefully. Then we cross-reference it against the human record going back thousands of years, the texts and the traditions and the documented observations left by people who watch the same sky we watch now. We do not preach, and we do not trade in fear. We report what is on the file, and we leave the interpretation where it belongs, which is with the person listening. If that is worth a quiet hour of the night, the subscribe button keeps the next report close, and we file a new one every night without fail. And we are always curious about the room on the other side of the screen, so before the data begins, tell us in the comments, where are you watching from tonight? The briefing begins. On the 15th of June, 2026, the Helmholtz Center Dresden-Rossendorf released the results of a study published the same day in the journal Nature Astronomy under the title of the timing of the last R process event near Earth, drawn from the deposition of 3 interstellar isotopes recorded in a deep-sea crust. The lead author is Dr. Dominik Koll of the Center's Institute of Ion Beam Physics and Materials Research. The senior author is Professor Anton Wallner, who heads the Accelerator Mass Spectrometry and Isotope Research Department at the same center. The team is international, with collaborators at the Australian National University in Canberra and at the Australian Nuclear Science and Technology Organisation, known as ANSTO, in Sydney. The sample at the heart of the work is a ferromanganese crust recovered from the floor of the Pacific Ocean. The measurement made on it concerns 3 radioactive isotopes: iron 6-0, plutonium 2-4-4, and curium 2-4-7. There is a number in tonight's data that no headline has carried, and it is not a measurement of something present, it is a measurement of something absent. The team searched this crust for the third of those isotopes, curium 2-4-7, using the most sensitive detection available anywhere in the world, and they did not find it. That absence is not a failure of the experiment. It is the single most informative result in the entire study, because the absence of that isotope is what allowed the team to put a date on the last event of its kind near our solar system. We will explain exactly how a thing that is not there can fix a moment in deep time. And then we will do one more thing with the date it reveals. We will set it beside 3 traditions on 3 different continents that reached the same conclusion about the heaviest metals long before any instrument existed to confirm it. How they arrive there, with no way to measure what we can now measure, is the question this report will answer by its end. Keep the missing isotope in mind. Everything tonight bends back toward it. Begin with the object itself, because the trustworthiness of the whole result rests on understanding what kind of archive a deep-sea crust actually is. Ferromanganese crusts form on the flanks of underwater mountains and ridges, at depths of hundreds to thousands of meters. In regions of the ocean, where the water moves slowly and very little sediment rains down to bury them, out of the seawater around them, atom by atom, they accumulate iron and manganese oxides, and as those oxides build up, they trap and hold whatever else happens to be drifting in the water, including the faint dusting of material that arrives at Earth from space. The crucial property is the rate. These crusts grow at a pace measured in a few millimeters per million years. That is slow, almost beyond intuition. A layer the thickness of a sheet of paper can represent tens of thousands of years of accumulation. A crust a few centimeters thick can carry an unbroken record stretching back more than 10 million years. And because the growth is so steady and the deep ocean so undisturbed, that record stays in order, oldest at the bottom, youngest at the top, like the pages of a book that has never been shuffled. The sample used in this study was not chosen at random. It is one of the best characterized ferromanganese crusts in the entire field of radionuclide research, a piece of seabed that has been studied before and whose growth history was already partly understood. Even so, the team did not take that history for granted. To read the cosmic isotopes correctly, they first had to know, with precision, how old each layer of the crust was. For that, they turned to a separate isotope, beryllium 10, which is produced steadily in Earth's own atmosphere and rains down into the ocean at a known and reliable rate. By measuring the beryllium 10 through the layers of the crust at the center's own facility in Dresden, and combining that with X-ray scans, three-dimensional imaging, and reference measurements on smaller drill cores, the team built a detailed age model. They worked out, layer by layer, how the crust had grown across more than 10 million years. Only once that timeline was secured could the cosmic isotopes inside each layer be placed at a real point in the past. This is the unglamorous foundation of the whole result, and it matters because a date is only as good as the clock behind it. Now to the first of the three cosmic isotopes, the one that is best understood and that anchors the study, iron 60. Ordinary iron, the iron in the planet's core and in the blood and in a cast iron pan, is stable. It does not decay. It comes in several stable forms, and those forms have been part of the Earth since the planet assembled out of the solar nebula 4.5 billion years ago. Iron 60 is different. Iron 60 is radioactive. It has a half-life of about 2.6 million years, which means that any given quantity of it loses half its atoms to decay every 2.6 million years. Run that forward and the consequence is stark. Iron 60 that was present when the Earth formed would have decayed away completely, many times over, within the first 100 million years of the planet's existence. There should be none of it left from the beginning. So if iron 60 is found in a layer of crust that is only a few million years old, there is only one reasonable conclusion. It did not come from the early Earth. It was delivered, recently in cosmic terms, from somewhere outside the solar system. And iron 60 has essentially one source in nature. It is forged in the cores of massive stars and flung out into space when those stars die as supernovae. Live iron 60 inches, a young layer of seabed is, in the plainest possible terms, supernova ash. This is not a new idea, and it is important to be clear that the supernova interpretation of iron 60 is solidly established and was not in question in this study. The discovery that deep-sea crusts carry a supernova signal goes back to work first reported in the late 1990s, and we will tell that longer story shortly. What this study adds to the iron 60 picture is detail and confirmation. The iron 60 inches this crust shows the distinct signatures of two separate near-Earth supernova events, both of them several million years ago. Two pulses, not one. That matches the broader scientific picture that has been built up over the past decade, in which our solar system appears to have been peppered by the debris of more than one nearby exploding star within the last 10 million years, as it drifted through a region of the galaxy that had been carved out and seeded by a whole series of stellar deaths. The iron, 60, in other words, behaves exactly as supernova debris should behave. It arrives in pulses, tied to specific explosions at specific times. Remember that word, pulses, because the second isotope is about to break that pattern, and the way it breaks it is the heart of tonight's finding. The second isotope is plutonium-244. On Earth, the word plutonium calls to mind reactors and weapons, the human-made isotope plutonium-239. Plutonium-244 is a different creature entirely. It is a naturally occurring isotope. It is not produced in any meaningful quantity by human activity, and it has a half-life of about 80 million years. That is far longer than the half-life of iron, 60, but on the scale of the Earth, it is still short. 80 million years sounds vast against a human life, yet against the 4.5 billion year age of the planet, it is a brief flicker. Whatever plutonium-244, the Earth was born with decayed away long ago. So, exactly as with iron, 60, any plutonium-244 found in a young layer of seabed cannot be left over from the planet's formation. It had to arrive from space, relatively recently, carried in on interstellar dust. The presence of live plutonium-244 inches, the crust is, on its own, evidence of recent cosmic delivery. But plutonium-244 is not forged the same way iron, 60, is. And this is where tonight's finding turns. Iron, 60, is made in the ordinary fusion processes inside massive stars and scattered by their supernovae. Plutonium-244 cannot be made that way at all. It is far too heavy. To build an atomic nucleus that large, you need a process that crams an enormous number of neutrons onto a seed nucleus in a very short span of time, faster than the nucleus can decay between additions. Physicists call this the rapid neutron capture process, or the R process for short. It is the mechanism responsible for roughly half of all the elements heavier than iron in the universe, and for essentially all of the very heaviest ones. Not only plutonium, but uranium, thorium, gold, platinum, and the rest of that company. The R process does not happen in the slow-burning core of an ordinary star. It requires conditions of almost unimaginable density and neutron flux, the kind of environment that exists for a fraction of a second when two neutron stars spiral into one another and merge, or possibly in a rare and especially energetic class of supernova. These are not common events. They are, by the reckoning in this study, something on the order of 1,000 to 10,000 times rarer than ordinary supernovae. So the team had, in a single crust, two cosmic isotopes made by two completely different kinds of event. Iron, 60 from conventional supernovae, plutonium-244 from the rare R process, and the obvious question, the question that organized the whole study, was simple. Do the two of them line up? If the same recent nearby explosions had delivered both, then the plutonium-244 should track the iron, 60, through the layers of the crust. The two should rise and fall together, peaking in the same layers, at the same depths, at the same moments in the past. That would tell a tidy story. A nearby explosion, a few million years ago, that made both the ordinary supernova debris and the heavy R process elements at once. That is not what the crust showed. The iron, 60, came in its two distinct pulses, sharp and tied to specific recent supernovae. The plutonium-244 did not. Instead of arriving in pulses, the plutonium-244 was present more or less continuously through the layers, spread evenly across millions of years like a faint, steady haze, rather than a series of distinct deliveries. The team's word for it is a veil. The plutonium did not fall in with the supernovae. It was already there, in the interstellar material the solar system has been moving through, distributed smoothly, the way a substance becomes distributed when it has had a very long time to mix and disperse. And that even distribution is itself a clock of a kind, because the only way for our process material to spread that smoothly through the local interstellar medium is for it to have been injected long enough ago that it had time to diffuse and even out. The plutonium-244, in short, is old, far older than the supernovae the iron 60 records. It is the residue of an R process event that predates the recent explosions by a wide margin. This is the point at which the third isotope, the absent one, becomes decisive, and the point at which we return to the question planted at the start of this briefing. To turn the plutonium-244 from a vague statement of age into an actual date, the team needed a second R process isotope to compare it against, one that decays at a different rate. That is where curium-247 comes in. Curium-247 is also made only in the R process, in the same kind of event that makes plutonium-244. The two are forged together, but curium-247 has a half-life of about 15.5 million years, far shorter than the roughly 80 million year half-life of plutonium-244, and there lies the leverage. If an R process event happened recently, both isotopes would still be present in their original ratio, because not enough time would have passed for either to decay much. But as time goes on, the curium-247, with its shorter half-life, vanishes far faster than the plutonium-244. The ratio between them is therefore a stopwatch. Measure how much curium-247 survives alongside the plutonium-244, and the ratio tells you how long ago the event occurred. A large surviving fraction of curium means a recent event. A vanishingly small fraction, or none at all, means the event was old. The team searched for cosmic curium 247 inches, the crust with the highest sensitivity any facility on Earth can currently bring to bear. This was, in itself, a milestone. It represents the first significant attempt ever made to measure cosmic curium-247 at all, and despite that sensitivity, they found none. The curium-247 was gone. All of it had decayed, and because curium-247 decays on a timescale of 15.5 million years, the only way for it to have vanished completely, while the longer-lived plutonium-244 still lingered as a faint veil, is for the R process event that made both of them to have happened a very long time ago. The plutonium that remains, set against the curium that does not, fixes the last major R process event near our solar system at a moment deep in the geological past, far older than the recent supernovae, the iron 60 records. There is a specific figure the team derived for that moment, and it is a figure with a particular resonance because it lands inside a chapter of Earth's history that almost everyone can picture. We are going to hold that figure for now. We will state it plainly and explain what it means when we reach the older record, because that is where it stops being only a date and starts being something stranger. For the purposes of the data on the board tonight, the conclusion is this. The iron is recent and arrives in pulses, the plutonium is old and arrives as a veil, and the curium is absent, and the absence is the clock. To understand the weight of that conclusion, it helps to slow down on what the R process actually is and where it happens, because this is the engine behind the entire study, and it is one of the more remarkable facts in all of physics. Almost everything around us is made of light elements. Hydrogen and helium were made in the first minutes after the universe began. The elements up to iron, the carbon in living things, the oxygen in the air, the silicon in rock, the iron in the planet's core, are forged by fusion inside stars, where lighter nuclei are pressed together to make heavier ones, releasing energy as they go. But that ladder of fusion stops at iron. Iron is the most tightly bound nucleus there is. Fusing iron into anything heavier does not release energy, it costs energy. So the ordinary furnace of a star cannot climb past iron. Everything heavier than iron, every atom of silver, tin, gold, lead, uranium, has to be built by a different route, by capturing neutrons rather than fusing nuclei. There are two ways to capture neutrons. The slow way, the S process, happens inside aging stars over long stretches of time, adding neutrons one at a time with long pauses between them, and it builds many of the moderately heavy elements. But the slow way cannot make the heaviest and most neutron-rich nuclei because the half-built nuclei decay before the next neutron arrives. For those, the rapid way is required, the R process, in which a nucleus is bombarded with neutrons so quickly, so densely, that it captures a whole cascade of them in less than a second, racing up the chart of the elements before it has any chance to fall apart. The R process is how nature builds the very top of the periodic table. It is the only way to make plutonium and curium and uranium and thorium, and it is responsible for a large share of the gold and platinum in existence. And it demands an environment of staggering extremity, a place flooded with free neutrons at densities and temperatures that almost nothing in the universe can supply. For decades, the leading candidate for where this happens was a particular and dramatic class of supernova. But in recent years, the picture sharpened, and the leading site became something even more exotic: the collision of two neutron stars. A neutron star is what remains after a massive star has died and its core has collapsed so completely that its protons and electrons have been crushed together into neutrons, packing the mass of the Sun into a sphere the size of a city. A teaspoon of neutron star material would weigh as much as a mountain. When two of these objects, locked in a death spiral, finally merge, they release a flash of energy that briefly outshines galaxies, and they fling out a cloud of neutron-rich matter in which the R process runs at full force, forging the heaviest elements in the moments of the collision and scattering them into space. Astronomers call the visible afterglow of such a merger a kilonova. The study released this month points squarely at this kind of origin. The conclusion of the team is that the plutonium in the crust came from a very rare cosmic explosion, the merger of two neutron stars or an exceptionally energetic supernova, and that the material has since dispersed throughout the interstellar medium around us. This is why the rarity matters so much, and why the number the team derived is so striking. Ordinary supernovae are not common, but on cosmic timescales they pepper a galaxy steadily, and our solar system has caught the debris of more than one within the last few million years, which is exactly what the Iron 60 records. Neutron star mergers are something else. They are perhaps 1,000 to 10,000 times rarer than ordinary supernovae. They are so rare that the matter they produce, once injected into a region of the galaxy, can sit there for an enormous span of time, slowly mixing into the general interstellar haze, with no fresh injection to renew it. That is precisely the behavior the plutonium-244 shows. Not pulses tied to recent events, but a thin, even veil, the long-settled residue of something that happened once, long ago, and has not happened again nearby since. The heaviest matter in our corner of the galaxy is, in a real sense, antique. It was made in a single ancient catastrophe and has been drifting and thinning ever since. There is a consequence of this that is worth stating plainly, because it reframes how we should think about the most ordinary precious objects. The reason gold is rare and precious on Earth is not a quirk of geology. It is a direct inheritance of the rarity of the events that make it. Gold is scarce because the R process is scarce. The metal in a ring, the metal that has been fought over and hoarded and buried with kings, is scarce on this planet for the same reason the plutonium veil in the crust is faint, because the cosmic forge that produces it almost never runs nearby. When we say tonight that the last major R process event near our solar system lies deep in the geological past, we are also saying something about why the heaviest treasures of the Earth feel the way they feel. They are the cooled and scattered fragments of a catastrophe that, in our neighborhood, has not been repeated in the span of time we will reach shortly. That fragment of perspective is one we will hand to the ancient record later tonight, because the people who first prized these metals reached, in their own language, for almost the same explanation. The measurement itself deserves attention, because the difficulty of it is hard to overstate, and because the credibility of the whole result rests on the instruments that made it. Consider what the team was attempting. Plutonium-244 arrives at Earth in quantities so small that a single atom of it hides among something like 10 sextillion other atoms. 10 sextillion is a 1 followed by 22 zeros. To find the plutonium, the relevant layers of the crust had to be chemically dissolved and processed down, separating out the vanishingly rare heavy atoms from the overwhelming bulk of ordinary matter, until what remained was a final sample in which only a handful of the target atoms were present. And then those atoms had to be counted, one at a time. As the leading scientist at the Sydney facility described the sensitivity, they need only about 100 atoms of plutonium in the final sample to capture one of them in the detector. That is, the order of precision required. Not parts per million, not parts per billion, but the detection of individual atoms drawn from an almost inconceivable sea of background material. The tool that makes this possible is accelerator mass spectrometry. rather than relying on waiting for a radioactive atom to decay and catching the particle it emits, which for these long-lived isotopes would take impractically long. Accelerator mass spectrometry counts the atoms directly. The sample is ionized, accelerated to high energy through a particle accelerator, and then sorted by mass and charged with such discrimination that the few atoms of the target isotope can be separated from everything else and registered individually. It is, in effect, a way of weighing single atoms and picking out the rare ones by hand. The technique has been refined over decades, and only its most advanced implementations can reach the sensitivity these cosmic isotopes demand. 3 facilities carried the work, and it is worth naming what each contributed because this is the monitoring infrastructure that turns a lump of seabed into a dated cosmic record. The plutonium and the curium measurements were made at the Vega facility at the Australian Nuclear Science and Technology Organization in Sydney. According to the team, Vega is currently the only facility in the world sensitive enough to detect cosmic traces at this level, which is why the search for curium-247, the first serious attempt of its kind, could be made there and essentially nowhere else. The iron-60 measurements were performed at the Heavy Ion Accelerator facility at the Australian National University in Canberra, a separate accelerator suited to that isotope. And the crucial dating work, the beryllium-10 measurements that established how old each layer of the crust was done at the DREAMS facility at the Helmholtz Center in Dresden. 3 accelerators on 2 continents, each handling the part of the problem it was built for, and a coordinating team in Germany stitching the results into a single timeline. This is what authoritative data looks like in this field. It is not one instrument and one number. It is several independent, highly specialized facilities cross-checking one another, with an explicit age model underneath, so that every atom counted can be placed at a real depth and a real moment in the past. The team also pushed the resolution of the plutonium measurement further than anyone had managed before. Rather than treating the crust as a single block and asking only whether plutonium was present, they divided the sample into individual layers, each containing only a few atoms of plutonium, and measured them separately. That is what allowed them to see the difference in behavior between the isotopes in the first place, to watch the iron-60 rise and fall in pulses, while the plutonium held steady across the layers as a veil. Without that layer-by-layer resolution, the central finding of the study, the decoupling of the supernova signal from the R-process signal, would have been invisible. It would have averaged out into a single blur. The ability to resolve it is recent. The capacity to detect cosmic curium-247 at all is recent. This is a large part of why a finding about an event more than 100 million years old could only be made now, in 2026, and not before. The event has been waiting in the crust the whole time. The instruments to read it have only just arrived. That number will matter when we reach the older record, so hold it for now. The point to carry out of the measurement is one of confidence. The result is not a single fragile reading that could be a fluke. It is built from 3 isotopes, measured at 3 world-class facilities, anchored to an independent age model, and resolved layer by layer through more than 10 million years of seabed. When the team states that the iron arrives in pulses, that the plutonium arrives as a veil, and that the curium is simply gone, those are not impressions. They are counts of individual atoms, made by the only machines on Earth currently capable of making them. It is reasonable to ask how matter from a dead star ends up locked in a rock at the bottom of an ocean at all, because the journey is long, and the answer is part of why these crusts are trustworthy archives. The heavy isotopes do not arrive as bare atoms drifting freely. They are bound up inside interstellar dust grains, tiny solid particles that form in the outflows of stars and in the debris of explosions, and then float through the galaxy for ages. As the solar system moves through a region seeded with such dust, some of those grains are swept inward. The larger and faster ones can survive the passage through the heliosphere, the bubble of solar wind that shields the inner solar system, and reach the Earth. There, the grains settle through the atmosphere, fall into the oceans, and drift down through the water column to the seabed, where the slow-growing ferromanganese crust scavenges them from the water, along with the iron and manganese it is already collecting. The cosmic isotopes become part of the crust's chemistry, fixed at the depth corresponding to the moment they arrived, and there they stay, shielded by kilometers of water from the disturbances of the surface world. This delivery mechanism explains a subtle feature of the iron 60 record that supports the supernova interpretation. The arrival of supernova debris is not instantaneous. After a nearby star explodes, its debris expands outward over thousands of years before the leading edge reaches the solar system, and the dust continues to wash over the Earth for a long stretch afterward as the cloud passes. So the iron 60 signal in a crust is not a single sharp spike at one instant, but a broadened pulse, rising and then falling over a span of time, exactly the shape that a passing cloud of supernova dust should produce. The crust records two such broadened pulses, the chemical echoes of two separate stars whose debris washed over the planet at two different times in the recent geological past. The shape of the signal, not only its presence, is consistent with the physics of how stellar debris travels and settles. It is one more reason the supernova reading is regarded as secure rather than speculative. The same logic, applied to the plutonium, is what makes its different shape so telling. If the plutonium had ridden in on the same recent supernova clouds as the iron, it too should show broadened pulses lining up with the iron 60. Instead, it shows the flat, continuous veil. The plutonium dust was not delivered by the recent passing clouds. It was already suspended, evenly, in the general interstellar material the solar system has been moving through for a very long time, mixed in so thoroughly that it dusts the crust at a roughly constant rate across the whole record, rather than spiking at any one moment. The delivery mechanism is the same. Dust grains scavenge from the water, but the distribution in time is completely different, and that difference in distribution is the signature of a completely different age. The recent supernovae shout, in two distinct pulses. The ancient R process event hums at a constant low level through every layer. The instruments can now tell the shout from the hum, and that, in a sentence, is what the study accomplished. A finding this large invites alternative explanations, and a careful team works to close them off before publishing. The most important one the group addressed has to do with where the solar system currently sits. Our sun is moving, right now, through a region of relatively dense gas and dust known as the local interstellar cloud, itself nestled inside a much larger and emptier zone called the local bubble, a cavity in the galaxy that was hollowed out and seeded by a series of supernovae over the last several million years. In recent years, some researchers have proposed that the solar system's passage into this denser cloud could itself account for an influx of certain interstellar isotopes that simply moving into thicker material might sweep up debris and deposit it on Earth. If that were the source of the plutonium, the story would be very different and far more recent. The team examined this possibility directly and was able to rule it out. The plutonium signal does not match what a recent passage into a dense cloud would produce. Its even distribution across millions of years of crust and the complete absence of the shorter-lived curium that a recent injection would still carry both point away from any recent delivery and toward an ancient origin. The veil is old, and a recent cloud crossing cannot fake that. There is a second strand of evidence that strengthens the interpretation, and it comes from an entirely different kind of instrument. In recent years, two neutron star merger events have been observed directly, not through their debris in a rock, but through the gravitational waves they sent rippling across space-time as they collided, picked up by detectors built for exactly that purpose. Those detections were landmark confirmations that neutron star mergers are real, that they happen, and that they forge heavy elements in the act. But both of the observed mergers occurred far outside our own galaxy, at distances so vast that none of their material will ever reach us. They are proof of the mechanism, not the source of our plutonium. What they establish is that the kind of event the team is invoking truly exists in the universe and does what the team says it does. What the crust adds is the local chapter, that such an event also happened once in our own cosmic neighborhood, long enough ago that only the longest-lived of its products still lingers, faintly, in the seabed and in the planet and in us. As this report is filed, the work is not finished, and the team has been explicit about what comes next, which is itself part of the monitoring picture. The first direction is the moon. Lunar samples returned by past missions and material expected from future ones are being looked to as another archive of the same isotopes, one without the complications of Earth's weather and oceans, and the team has pointed to NASA lunar samples as a way to study the last R-process event in finer detail. The Moon has no atmosphere to filter what falls on it, and no oceans to redistribute it, which in principle makes it an even cleaner ledger than a deep-sea crust. The second direction is a new instrument. The team has noted that a new facility under development in Dresden, referred to as Hamster, is expected to reach a sensitivity comparable to the Sydney Accelerator, which would mean that the detection of these almost impossibly rare cosmic atoms, currently possible at essentially one place on Earth, would no longer depend on a single facility. The hunt for plutonium, curium, and other rare radionuclides would have a second home, and the kind of measurement that produced tonight's result could be repeated, checked, and extended. The capability that made this finding is, in other words, about to widen. It is worth pausing on what the iron 6-0 side of the record says about our own recent past, because it puts the ancient R-process event in context, and it concerns the planet directly. The two supernova pulses recorded in the crust are not abstractions. They mark two occasions, within the last several million years, when stars died close enough to our solar system to dust the Earth with their debris. Close, in this context, does not mean close enough to sterilize the planet. The events were far enough away that life carried on, and no mass extinction has been firmly tied to them. But they were near enough to leave a measurable layer of stellar ash across the floor of every ocean, near enough that the night sky of our distant ancestors, the early members of our own genus, may have briefly held a star brighter than any other, blazing for weeks before fading. The iron 6-0 is the residue of those deaths. It tells us that the neighborhood we live in has been, in the recent geological past, an active one, shaped by exploding stars. And against that backdrop of relatively recent, relatively ordinary stellar deaths, the plutonium veil stands out all the more sharply because it speaks of something that has not happened recently at all, something rarer and older, the last time the rarest forge of all ran close enough to leave its mark. We have, then, a complete picture on the board, a patient archive on the floor of the Pacific, 3 cosmic isotopes, 2 found and 1 telling absence. Iron 60 inches, 2 recent supernova pulses. Plutonium 244 inches, an old even veil. Curium 247 gone, and the gap it leaves serving as a clock. An R-process origin in the rarest catastrophe, the universe stages, the merger of dead stars. A measurement made at the edge of what instruments can do, at facilities on 2 continents, anchored to an independent timeline. And a single conclusion about when the heaviest matter near us was last forged, a conclusion we are holding back by one deliberate beat, to be set down where it belongs, beside the older record. That is the data. The interpretation, as always, comes next, and it begins not with the instruments, but with the long human effort that led to them. The recent supernova record deserves a fuller account, because it is the established floor on which this new finding stands, and because it shows how reliably a deep-sea archive can recover the deaths of nearby stars. The 2 iron 6-0 pulses in this crust correspond to a pattern that has been pieced together across many studies and many ocean samples. The clearest of the signals points to a nearby supernova that scattered its debris across Earth somewhere around 2.5 to 3 million years ago, with a second, older enhancement further down in the record, reaching back towards 6 to 7 million years ago. These are not isolated quirks of one rock. The same iron 6-0 enhancement at around 3 million years has been recovered from sediments and crusts in different ocean basins, from material on the Moon, and even in measurements of cosmic rays, a convergence of independent archives that leaves little doubt that the events were real and that the debris reached the whole inner solar system. The setting for these explosions is the local bubble, and understanding it changes how the recent supernovae should be pictured. Our solar system currently sits inside a vast, low-density cavity in the interstellar gas of the galaxy, a bubble roughly hundreds of light-years across that was blown open by a long series of supernovae over the past 10 to 15 million years. The stars responsible are thought to have belonged to associations of young, massive, short-lived stars, the kind that burn fast and die violently, drifting through this part of the galaxy in groups. As each one exploded, it added its energy to the expanding cavity and its debris to the thin gas inside it. The solar system did not make this bubble. It wandered into it and is passing through it now. The two iron 60 pulses are the fingerprints of two of the more recent and nearer of those explosions, the ones that detonated close enough for their ash to settle measurably onto Earth. So the recent supernova history written in the crust is, in effect, the local weather report of a stellar neighborhood that has been unusually active, a region still ringing from a sequence of nearby deaths. What those nearby supernovae did to Earth is a question scientists treat with care, and it is worth relaying that care rather than overstating it. The events were close enough to leave a clear chemical mark, but the evidence does not support the idea that they caused any catastrophe at the surface. No mass extinction has been firmly tied to them. What researchers have explored, in the measured language of the literature, are subtler possibilities. A temporary rise in the cosmic radiation reaching the upper atmosphere, potential effects on cloud formation or climate, a possible nudge to the biosphere during a period when the planet was already cooling toward the ice ages. These remain areas of active study rather than settled conclusions, and a responsible account leaves them as open questions. The firm part is the chemistry. The iron 60 is unambiguous, the timing is reproducible across archives, and the conclusion that two nearby stars died within the last several million years is as solid as anything in this field. The speculative part, the question of consequences for life, is exactly the part where the honest answer is that the work is ongoing. Set the recent supernova record beside the plutonium veil, and the contrast is the whole point of tonight's study. The supernovae are recent, repeated, and traceable to specific moments. They are, in cosmic terms, local news. The R process event behind the plutonium is none of those things. It is single, ancient, and smeared across the record rather than spiked at one depth. If the recent supernovae are the neighborhood's weather, the plutonium veil is closer to the bedrock, a deep and settled layer left by a far older and far rarer event. The genius of using two R process isotopes together, the surviving plutonium and the vanished curium, is that it lets the team reach past the noisy recent supernova activity to date, that deeper, quieter event, the one the ordinary supernova record cannot touch. The recent stellar deaths and the ancient R process catastrophe are two different stories written in the same rock, and the new measurement is what finally pulled them apart. There is one more reason the local bubble context matters for tonight, and it points forward. The solar system's motion through this region is ongoing. We are still inside the bubble, still passing through the denser cloud within it, and the interstellar material around us still carries the faint, well-mixed residue of that ancient R process event. The plutonium veil is not only a thing of the past preserved in old rock. In a small way, it is still arriving, still settling out of the local interstellar medium onto the planet, a thin and continuous fall of the oldest heavy matter in our corner of the galaxy. The crust caught millions of years of it. The fall has not entirely stopped. We are, even now, moving through the long dispersed ash of a catastrophe that lit the local sky before the dinosaurs were gone. It is worth laying out, carefully, the full ladder of where matter comes from, because the R process sits at the very top of it, and tonight's finding is ultimately a statement about the origin of the heaviest rungs. In the first minutes after the universe began, only the lightest elements formed: hydrogen, most of the helium, and a trace of lithium. Everything else, every heavier atom in existence, was built later, inside stars and in the depths of stars. For billions of years, generations of stars have fused hydrogen into helium, helium into carbon and oxygen, and on up through the lighter elements, seeding each new cloud of gas with the products of the last generation before collapsing into the next. This is the slow assembly of the periodic table, and it accounts for the bulk of the ordinary matter around us. The carbon and oxygen and nitrogen of living things, the silicon and magnesium of rock, the calcium and bone. That assembly line runs efficiently right up to iron and then halts, for the reason given earlier. Iron is the most stable nucleus, and building anything heavier costs energy rather than releasing it. So, the elements beyond iron required nature to find other methods, slower and rarer and stranger. The slow neutron capture process, operating inside aging stars over thousands of years, fills in a good share of the middleweight heavy elements, the likes of strontium, barium, and lead, by adding neutrons gently, one at a time, with long waits between. But for the heaviest and most neutron-rich nuclei, the slow process is simply too slow. The half-finished nuclei decay before they can grow. Only the rapid process, the R process, with its violent flood of neutrons captured in under a second, can carry a nucleus all the way to the top of the chart and hold it there long enough to survive. The roll call of what the R process makes is, in a sense, the roll call of the most coveted and most dangerous substances on Earth. Much of the world's gold, much of its platinum and the metals that travel with it, the rare earth elements that sit at the heart of modern electronics, and the actinides, the heavy radioactive family that includes uranium and thorium, the elements whose slow decay heats the interior of the Earth and drives the convection that moves continents, along with the plutonium and curium the team measured in the crust. When the study speaks of new insights into the formation of the heaviest elements in the universe, this is the territory it means. The plutonium and curium are not just exotic tracers chosen for convenience. They are members of the same family as the gold and the uranium, forged by the same rapid process in the same kind of catastrophe, and counting them is a way of dating the last time that whole family was minted nearby. This is why a finding about 2 faint isotopes in a deep-sea rock reaches so far beyond the rock. It is a measurement of when our corner of the galaxy last ran, the cosmic forge that produces the heaviest treasures and the heaviest hazards alike. It connects the gold in the ground to a specific, datable category of event. It says that the reason these elements are scarce is that their birthplace is scarce, and it begins to fix, with real numbers, just how long ago the local birthplace last operated. The periodic table, seen this way, is not a static chart on a classroom wall. It is a record of cosmic history, and its top rows are signed by events as rare as the merger of dead stars, events the crust in the Pacific has now helped to date. A word, finally, on how the team kept the measurement honest, because there is a specific trap in plutonium work that has to be avoided, and the way around it is part of why this particular isotope was chosen. Plutonium is not only a cosmic substance. The 20th century filled the surface of the entire planet with man-made plutonium, scattered by atmospheric nuclear weapons testing, and that fallout is overwhelmingly composed of the isotopes plutonium-239 and plutonium-240. Any attempt to detect a faint cosmic plutonium signal has to contend with that human-made background, which is present in trace amounts almost everywhere on Earth. The escape from the trap is the choice of isotope, plutonium-244. The isotope at the center of this study is essentially not produced by nuclear weapons. It is not part of the fallout signature. So, a plutonium-244 atom found in the crust is not contamination from the bomb era. It is, with high confidence, a genuine arrival from space. The team's decision to track plutonium-244 specifically, rather than the more abundant fallout isotopes, is precisely what allows the cosmic signal to be read cleanly against the noise of the modern world. The same logic underlies the use of iron, 60, and curium-247. Isotopes chosen because they have no significant terrestrial or human source, so that their presence can mean only one thing: that care. The deliberate selection of isotopes with no earthly origin, the layer-by-layer resolution, the independent dating, the cross-checking across 3 facilities, and the explicit closing off of the dense cloud alternative is what lifts this from an intriguing reading to a result the field can stand behind. The conclusion the team reached is not loosely argued. It is the careful product of choosing exactly the right messengers and reading them with the only instruments precise enough to hear them. It is worth dwelling, in concrete terms, on the violence that forges this matter, because the scale of a single R process event is difficult to hold in the mind, and it reframes the faintness of the veil. When 2 neutron stars merge, the energies involved are at the limit of what the universe produces, short of the explosions of the largest stars and the feeding of black holes. 2 objects, each more massive than the sun, yet each only the size of a city, circle one another faster and faster, thousands of times a second in their final moments, until they touch and tear apart. In the instant of the merger, a portion of that ultra-dense, neutron-rich matter is flung outward at a sizable fraction of the speed of light, and in that expanding cloud the R process runs to completion, building the heaviest elements in roughly the time it takes to read this sentence. The afterglow, the kilonova, is powered by the radioactive decay of the freshly minted heavy elements themselves, glowing for days to weeks as the new matter settles. The estimates that astronomers have placed on how much heavy material a single such merger can produce are staggering. A single neutron-star collision is thought to be able to forge many times the mass of the Earth in heavy elements, including quantities of gold and platinum that dwarf anything in our entire solar system. One event, many Earth masses of gold scattered into space in an afternoon. And yet, against the size of the galaxy and the rarity of these collisions, even that titanic output thins to almost nothing by the time it has spread through the interstellar medium and drifted for 100 million years or more. That is the reconciliation tonight's data forces on the imagination. The event that made the plutonium in the crust may have produced more gold in a moment than exists in all the vaults and all the ore bodies of the Earth combined. And what reaches us across the gulf of time and space is a veil so faint that detecting it requires counting individual atoms one by one. The grandeur of the source and the faintness of the trace are two sides of the same fact. The forge is real, the forge is enormous, and the forge runs so seldom and so far away that its products arrive here as a whisper. This is the texture of the cosmos that the study quietly exposes. Abundance at the source, scarcity at the destination, and an immense span of time in between. There is a further wrinkle that touches the Earth's own treasure directly, and it is worth stating plainly, while noting that it sits at the frontier of active research. When the Earth formed and was still molten, most of the gold and platinum it inherited from the interstellar cloud should have sunk, along with the iron, into the core, leaving the rocky outer layers nearly stripped of these metals. Yet the crust and mantle hold more gold and platinum than that simple picture predicts. One leading explanation is that a late rain of impacts, after the core had already formed, delivered a fresh coating of these metals to the outer Earth, a so-called late addition that left the accessible gold near the surface where, billions of years later, it could be mined. Whether or not that account holds in every detail, the deeper point stands and connects directly to tonight's finding. The gold within reach of human hands traces back, through the building of the solar system, to our process events that occurred before the sun existed. The crust in the Pacific and the gold in a mine are entries in the same ledger. Both are accountings of how the heaviest matter, made in rare catastrophes across the history of the galaxy, found its way into this planet and onto its surface. As this report is filed, then, the situation is this. The solar system continues its drift through the local bubble and the denser cloud within it, still sweeping up the thin, ancient residue of an R-process event that predates the dinosaurs. In a deep-sea crust on the floor of the Pacific, that residue has now been read, layer by layer, and dated by the clock of a missing isotope. At facilities in Sydney, in Canberra, and in Dresden, the capability that made the reading possible is being extended, with a new German accelerator approaching the sensitivity of the Australian one, and with lunar samples lined up as the next, cleaner archive to consult. The instruments are running, the measurement stands, and the single number it points to, the moment when the heaviest matter near us was last forged, waits in the wings of this report, because the place to set it down is not here, among the accelerators, but later, beside the older record, where the same conclusion was reached in a different language entirely. That is the full briefing, and it is, in the end, an account of human patience as much as cosmic violence. No team reaches a result like this in a single stroke. It rests on 3 decades of incremental, frequently unnoticed work, a chain of discoveries running from the first faint hint that a rock could hold a supernova to the night the heaviest elements were caught being born. That chain is the historical record this report turns to next, and it has its own names, its own dates, and its own quiet drama. No result like this arrives without a lineage, and the lineage here is roughly 3 decades long. It begins in the late 1990s, in Germany, with a physicist named Klaus Knie and colleagues working under Günter Korscheneck at the Technical University of Munich. The idea they were testing had been floated a few years earlier, almost as a thought experiment, that if a star had exploded close to the solar system in the geologically recent past, its debris might have left a faint, radioactive fingerprints somewhere on Earth, a layer of an isotope that the planet could not have made on its own. The candidate was iron, 60. The place to look was a deep-sea ferromanganese crust. In 1999, and in a refined measurement reported in 2004, the Munich group announced that they had found it, a measurable enhancement of live iron 60 inches, a crust layer corresponding to roughly 2 to 3 million years ago. It was the first physical evidence that a supernova had gone off near enough to dust the Earth and that the event was recent enough to still be readable. A single isotope in a single rock had turned a hypothesis into a measurement. Hold the shape of that first discovery in mind, because the study released this month is its direct descendant, using the same kind of archive and the same logic, only reaching for far rarer isotopes and a far older event. The line runs straight from that crust in Munich to the crust in Dresden. It is worth appreciating how unlikely that first detection seemed at the time. Accelerator mass spectrometry was still maturing, and the quantity of iron, 60, the group was claiming to have found amounted to a handful of atoms separated from a crust by painstaking chemistry. The natural reaction in any careful field is doubt, and there was doubt. A signal that faint, drawn from a rock that had spent millions of years on the ocean floor absorbing whatever drifted past, could in principle have come from contamination, from a measurement artifact, from any number of mundane sources that would be far more probable than a nearby exploding star. What carried the claim from curiosity to acceptance was repetition and refinement. The Munich measurement was tightened, the timing was pinned more firmly to a layer corresponding to the recent geological past, and the result held up. The pattern that would define the entire field was set in that first chapter. An extraordinary claim, a faint signal, a slow and skeptical process of confirmation, and a rock that turned out to be telling the truth. Every later chapter, including the one written this month, follows that same arc. The second chapter came in 2016, and it widened the picture from a single event into a pattern. In April of that year, the journal Nature carried a pair of studies that together reshaped the field. One, led by Anton Wallner, the same physicist who would later anchor tonight's work, gathered iron, 60 measurements from deep-sea sediments and crusts drawn from oceans around the world, and showed that the supernova signal was global and that it came in more than one episode, pointing to multiple nearby supernovae over the past 10 million years rather than a single isolated blast. A companion study modeled where those explosions had come from, tracing them to a drifting association of massive young stars and tying the whole sequence to the formation of the local bubble, the cavity in the galaxy our solar system now occupies. In the same period, another team reported finding iron 60 inches lunar samples returned by the Apollo missions, confirming that the debris had fallen not only on Earth but across the inner solar system. What had been one rock in one event was now a coherent history of a stellar neighborhood, written in iron, recovered from the ocean floor, the moon, and even the stream of cosmic rays. That last archive is worth a sentence of its own, because it is so unexpected. In the same era, a spacecraft instrument measuring the composition of galactic cosmic rays, the high-energy particles that stream constantly through the solar system, reported capturing individual nuclei of iron, 60 among them. Iron, 60 was being detected not only as a fossil in ancient rock, but as a live particle still in flight through nearby space, fresh enough to have survived the journey, more evidence that the material of recent supernovae is truly present in our corner of the galaxy and still moving through it. The source of the recent explosions, meanwhile, was traced to a drifting group of massive stars, an association lying within a few hundred light-years, whose members have been dying off one by one over millions of years. The modeling suggested the nearest of the relevant explosions detonated at a distance comfortably outside the range that would threaten life on Earth, yet close enough to leave the iron signal in every ocean. There is a number worth carrying forward from that chapter. The supernovae it identified were close, in the range of a few hundred light-years, near enough to leave a mark, but far enough to spare the biosphere. We will set that distance against something the ancient record preserves before the night is done, because one tradition appears to have recorded a star changing in a way that modern astronomers can identify, and the question of what people see when a star nearby begins to die is older than any instrument. The third chapter is the one that turned a deduction into a direct sighting, and it did not come from a rock at all. It came on the 17th of August, 2017, when gravitational wave detectors registered the unmistakable signal of two neutron stars spiraling into one another and merging in a galaxy roughly 130 million light-years away. Within hours, observatories across the planet swung toward the location, and for the first time in history, a neutron-star merger was watched directly across the spectrum of light. As it unfolded, what they saw was a kilonova, the glowing afterglow predicted by theory, and embedded in its light were the spectral signatures of freshly forged heavy elements, including the unmistakable mark of newly made strontium. It was the first time anyone had caught the heaviest elements being born, in real time, in the very kind of event theorists had argued was responsible. The forge had been seen running. After 2017, the claim that neutron star mergers make the heaviest matter in the universe was no longer an inference. It was an observation. The detail of that night is worth keeping, because it stands as one of the high points of modern astronomy. The gravitational wave signal lasted about 100 seconds as the two neutron stars wound toward collision, and roughly 2 seconds after they merged, orbiting telescopes registered a short burst of gamma rays from the same patch of sky, the first time a gravitational wave source and a flash of light had been tied to a single event. In the hours and days that followed, something on the order of 70 observatories around and above the Earth turned to watch the fading glow, tracking it across radio waves, infrared, visible light, ultraviolet, and X-rays. From the color and evolution of that glow, astronomers estimated that the single merger had forged a quantity of heavy elements amounting to many times the mass of the Earth, including, by some estimates, several Earth masses of gold and platinum alone. One collision, in a galaxy more than 100 million light-years away, had manufactured more precious metal in a moment than exists in the entire crust of our planet. That is the kind of event tonight's Crust says also occurred once, near us, in the deep past. Keep that night in mind, because tonight's study leans on it. When the team behind the Crust measurement says the plutonium came from a neutron star merger or an exceptionally energetic explosion, they are pointing at the same kind of event that was watched directly in 2017. The 2017 sighting proved the mechanism exists and does what is claimed. The 2026 Crust proves that such an event also happened once in our own neighborhood long ago. One is the universal proof. The other is the local case file. The fourth and final chapter is the immediate bridge to the present. Around 2021, the broad collaboration that includes Anton Wallner reported detecting live plutonium-244 alongside iron 60 inches, a deep-sea crust, and noted something that did not quite fit the simple story. The quantity of plutonium was lower than a tidy supernova picture would predict, a hint that the heaviest elements might be the product of rarer and more peculiar events than ordinary stellar explosions. That hint is exactly what the study released this month set out to test and resolve by adding the second R process isotope, curium-247, and using the absence of it to date the event. Tonight's result is the completion of a question first raised half a decade ago and a method first proven a quarter century ago. It is the latest entry in a record that has been building, patiently, one rock and one isotope at a time, since before many of the people now watching the sky were born. The 2021 finding deserves its weight because it is the hinge on which the whole present study turns. Detecting plutonium 244 inches a deep-sea crust at all was a feat, given that a single atom of it sits among that almost unimaginable sea of ordinary matter. But the surprise was not merely that it was there. It was that there seemed to be too little of it, and that what there was did not line up neatly with the iron 60 inches the way a single shared supernova source would demand. That mismatch was a loose thread, and a loose thread in a careful field is an invitation. It implied that the plutonium and the iron might not share an origin at all, that the heaviest elements might trace to something rarer than the supernovae the iron recorded. Pulling that thread is precisely what the team did over the following years, and the tool they reached for was the second R process isotope, curium-247, whose faster decay could convert a vague suspicion of age into a hard number. The study released this month is the knot at the end of that thread, tied off at last. That is the modern pattern. then, clear and well documented, a 30-year climb from the first faint iron, 6-0, through a global map of nearby supernovae, to the direct sighting of the cosmic forge in 2017, to the dating of our own ancient R-process event in 2026. The pattern in the modern record is clear. But we do not stop at the modern record. There is an older layer beneath it, older than accelerators, older than telescopes, older than the idea of an isotope, a layer of texts and oral traditions and recorded observations in which people who could measure nothing nonetheless arrived at the conviction that the precious metals were the substance of the sky and the relics of catastrophe in the heavens. That layer is what comes next. The modern record, for all its accelerators and its isotope ratios, arrived at a single underlying claim that the heaviest and most precious matter on Earth was forged in the sky, in rare catastrophe, and fell to us across an enormous reach of time. What we find when we turn to the older record is that this claim is not new. It is one of the oldest intuitions our species has written down. Across cultures that never met, on continents with no contact, people who could not have known a single fact of nuclear physics nonetheless concluded that gold and the bright metals were not truly earthly things, that they belonged to the sun, to the heavens, to the gods, and in some cases, that they were the leavings of violence in the sky. They were not measuring, they were reasoning from what they could see, and from the strange behavior of the metals themselves. And the conclusion they reached has an uncanny resemblance to the one the Crust confirmed this month. We will take 4 of these traditions in turn, name their sources, and then return to the number we have been holding back, because it is in the company of these traditions that the number finally means something. Begin in Egypt, where the association between gold and the divine was not a poetic flourish but a settled element of religious doctrine maintained across thousands of years. To the Egyptians, gold was not merely valuable. It was the very substance of the gods and of the sun. The flesh of the gods, the texts state plainly, was made of gold. In the body of religious literature that includes the pyramid texts, the oldest substantial corpus of religious writing from the ancient world, and that continues through the funerary compositions later gathered under the name the Book of the Dead, the divine body is described in mineral terms. The flesh of the gods is gold, their bones are silver, and their hair is the deep blue stone lapis lazuli. This was a description of what the gods were made of, and gold sat at the center of it because gold shared the 2 qualities the Egyptians most associated with divinity. It did not tarnish, corrode, or decay, which made it a fitting substance for beings who did not die, and it shone with the color of the sun. That second quality bound gold specifically to Ra, the sun god, the source of light and life. Gold was, in a real sense, solar matter, the metal that carried the sun's own color and the sun's own permanence. The temples sheathed the tips of obelisks and the surfaces of sacred objects in gold so that they would catch the first light of dawn and blaze like the sun itself. The pharaoh, the living link between the human and the divine, was buried in gold because gold was the material of the eternal and the celestial, the substance that would carry him into the company of the imperishable. When we read that the death mask of a king was wrought in gold, we are looking at a theological statement as much as a display of wealth. The king's mortal face was being replaced by a face of the same substance as the gods and the sun, a face that would not decay because the metal it was made of did not decay. Consider how close this sits to what the modern data says, stripped of its religious language. The Egyptians identified gold as a substance that belonged to the sun and the sky rather than to the ordinary earth, a substance categorically different from common matter, marked out by its permanence and its solar color as something celestial in origin. They could not have known that gold is in fact forged in the sky, in the depths of stars, and is in a literal sense not a product of the earth at all. They reasoned from what gold does. It does not rot, it does not rust, it holds the color of the sun, it behaves like nothing else in the mineral world. From that behavior they concluded that it must be of the heavens. The reasoning is not physics, but the destination is remarkably near the truth. Gold is celestial matter. The Egyptians said so in the language of gods, and the Crust in the Pacific says so in the language of isotopes, and the 2 statements point at the same fact from opposite ends of human history. There is a further detail worth drawing out, because it sharpens the parallel. The Egyptian conception held gold to be not only solar but incorruptible, beyond the reach of the decay that claims all earthly things, and this incorruptibility was the proof of its divine nature. In the modern account, gold's near indestructibility is likewise central. Gold is chemically inert. It resists the reactions that consume other metals, which is why ancient gold artifacts emerge from tombs still bright after thousands of years. The Egyptians treated that permanence as evidence of a heavenly origin, reading the same property the modern chemist reads, and drawing from it a conclusion about where the metal belonged. Gold endures, and that endurance set it apart in the Egyptian mind as a thing of the sky. Cross now to the Andes, to the empire of the Inca, where the same conviction took a different and even more vivid form. In the Andean world, gold and silver were understood through the two great celestial bodies, the sun and the moon, and the language used to describe them was not the language of commerce, but the language of the heavens shedding part of themselves onto the earth. Gold was called the sweat of the Sunday, silver was called the tears of the moon. These were not casual metaphors. They were the accepted account of what the metals were and where they came from, woven into a religious and political order in which the ruling Inca was regarded as the son of the sun, and the metals were sacred substances belonging, by right, to the celestial deities and their earthly descendants. We are not reconstructing this from fragments. It is preserved in some of the most important written sources on the Inca world, set down in the decades after the Spanish conquest. The chronicler Garcilaso de la Vega, himself the son of a Spanish father and an Inca noblewoman, recorded the Andean understanding of the metals in his Comentarios Reales de los Incas, his royal commentaries of the Incas, published in 1609, a work that remains one of the foundational accounts of Inca civilization, written by someone with direct access to its traditions. Other Spanish chroniclers of the same era, among them Pedro Chiesa de León and Juan de Betanzos, who married into Inca nobility and gathered testimony directly from Andean sources, recorded the same reverence for gold and silver as celestial substances tied to the sun and moon. Across these independent colonial accounts, the picture is consistent. The metals were understood as having descended, in some sense, from the sky, as the bodily issue of the sun and the moon themselves. Hold the phrase against the modern finding, because it is almost startling in its aptness. The sweat of the Sunday. The Andean tradition located the origin of gold not in the ground, where it was mined, but in the sun, a body in the sky, and imagine the metal as something the celestial body had given off that had then come to rest in the earth. The modern account says that gold is forged in stars and stellar catastrophe, given off by bodies in the sky, and deposited, eventually, in the earth. The Andean image of a heavenly body sweating out the precious metal, which then settles into the world below, is a mythic compression of exactly the process the isotopes describe. Heavy elements produced in the sky, released, and laid down in the rock. The Inca did not know the sun could not actually make gold, that the true forge is rarer and stranger and older than any star now shining. But they had placed the origin of the metal in the heavens and the deposition of it in the earth, and in doing so, they had captured the essential shape of the truth. There is something further in the Andean case that the other traditions sharpen by contrast, and it concerns the relationship between the metal and the body that produced it. Sweat and tears are not the main substance of the body that sheds them. They are a byproduct, a small excretion, a trace given off in the course of the body's existence. The Andean image, read closely, casts gold and silver as mere traces of the sun and moon, faint leavings rather than the bulk of those bodies. This is, again, uncannily faithful to the modern picture. The heavy elements are a vanishingly small fraction of what the cosmos produces. The plutonium in the crust is a faint veil, a trace, the merest excretion of an event whose main output was energy and light on a scale beyond comprehension. The Andean tradition framed the precious metals as the trace shed by a celestial body, and the modern data frames them as the faint residue of a celestial catastrophe. The proportion is right. The metals are the byproduct, the sweat, the tears, the thin leavings of something vast in the sky. That the Spanish, arriving with their own hunger for gold, recorded these beliefs, even as they melted down the sacred objects that embodied them, is one of the harder ironies in the history of the metal. The conquistadors saw bullion. The Andean world had seen the sweat of a god. Both were looking at the same substance, and only one of them had placed its origin in the sky, where, we can now say, it truly began. Travel now to the country where two of tonight's three accelerators sit, to Australia, and to a tradition that does something the others do not. The Egyptian and the Andean records tell us how people understood the metals. The Aboriginal record we turn to now appears to preserve the direct observation of a star in the act of changing, a stellar event witnessed, named, and remembered. And it pays off a thread we left open in the modern record. We noted there that the question of what people see when a star nearby begins to die is older than any instrument. Here is a case where the seeing was written down. The tradition belongs to the Burong people, a group of the Wurgaya-speaking country in the northwest of what is now the state of Victoria, who were renowned among their neighbors for the depth of their knowledge of the night sky. In 1857, a settler named William Stanbridge, who had built a relationship with the Burong and learned a portion of their astronomy, recorded what they told him about the stars and presented it to a learned society in Melbourne, leaving one of the most detailed early written accounts of an Aboriginal astronomical system. Among the many stars and figures the Burong named was one they called Collaborators War, described as a large red star, the wife of War, who was the crow, the star we know as Canopus. Collaborators War was given as a great star in a particular region of the sky, marked out as notable, large, and red. Here the modern and the ancient meet in a way that is rare and specific. In 2010, researchers in the field of cultural astronomy, examining Stanbridge's record against the astronomical history of the relevant patch of sky, proposed an identification. That Collaborators War corresponds to the star we call Eta Carinae. Eta Carinae is no ordinary star. It is a colossal, unstable system that in the middle of the 19th century underwent what astronomers call its Great Eruption, a vast outburst that, around the early 1840s, swelled it into one of the brightest stars in the entire southern sky, a brilliant red point that blazed for years before fading. This was a star in the throes of near destruction, a massive star convulsing in a way that foreshadows the kind of death that seeds the heavens with heavy elements. And the timing aligns with the period in which the Burong knowledge was alive and being passed on. The proposal, advanced carefully and within the normal caution of the field, is that the Burong observed Eta Carinae during or around its great eruption, recognized it as a significant new presence in the sky, and incorporated it into their tradition as the large red star Collaborators War, the wife of the crow. Consider what that means in the context of tonight. The modern record tells us that nearby dying stars have dusted the earth with their debris, and that the night sky of the past has, at times, held a star suddenly brightened by its own violence. The Burong tradition, if the identification holds, is a human record of exactly such a moment, a massive star flaring toward its end, observed and remembered by people watching the same sky from the ground. They had no theory of stellar evolution, no concept of an eruption or a supernova, no way to know that such convulsions are part of how the heavy elements are made. But they saw a great star change, they marked it as significant, and they fixed it in their knowledge of the heavens. Where the Egyptian and Andean traditions reasoned about the metals, the Burong tradition watched the sky and recorded a stellar cataclysm in progress. It is the observation layer of the same story, the human eye catching the very kind of event the isotopes record after the fact. There is a sober note to add, and the field that proposed the identification adds it too. Aboriginal Australian knowledge systems are among the oldest continuous traditions of observation on the planet, sustained orally across an immense span of time, and the loss of so much of that knowledge through the disruptions of the colonial period means that what reached Stanbridge's page is a fragment of a far larger whole. Even so, that fragment appears to hold the memory of a real star convulsing in the 19th century sky. The watching of the heavens and the recording of their changes is among the oldest things our species does, and on at least one occasion, in the country where tonight's instruments now stand, it caught a star coming apart. The fourth tradition is Greek, and it is the one that comes closest to a scientific claim, because it was advanced not as religion, but as natural philosophy, by a man who paid for it. In the 5th century before the Common Era, the philosopher Anaxagoras of Clazomenae proposed a set of ideas about the heavens that were, for his time and place, close to heresy. He argued that the sun was not a god but a thing, a vast incandescent mass of fiery stone or metal, glowing white-hot, larger, he is reported to have said, than the whole of the Peloponnese. He held that the moon was a body of earth and stone that shone only with reflected light, and that the stars too were fiery stones, carried in the heavens, made of the same kind of material as the ground beneath one's feet. In Anaxagoras' cosmos, there was no fundamental divide between the substance of the sky and the substance of the earth. The heavens were made of stone and metal, the same stuff as the world, only hotter and satellite. This was a dangerous thing to say in classical Athens, where the celestial bodies were divine, and Anaxagoras was, according to the ancient accounts, charged with impiety in part for teaching that the sun was a stone rather than a god. But the part of his thought that matters most for tonight is the claim that follows from it. If the heavens are made of stone and metal, then stones can fall from the heavens. And Anaxagoras is tied, in the ancient record, to a specific event that appeared to confirm exactly this. Around the year 467 before the Common Era, a great stone fell from the sky near Aegospotami, in the region of the Hellespont, a mass large enough to be remarked upon for generations afterward. The ancient sources report that this fall was associated with Anaxagoras, some of them even claiming, in the embellishing way of later legend, that he had predicted it. We do not need the prediction to be true to see the significance. A philosopher had argued that the sky was made of stone and metal, and a stone had fallen out of the sky, and the two were joined together in memory as evidence that the heavens and the earth were of one substance. We are not relying on a single thread for this. The fall at Aegospotami and Anaxagoras' teachings about the celestial bodies are reported across several of the major ancient authors. The Greek biographer Plutarch describes the fall of the stone and its connection to Anaxagoras in his Life of Lysander. The biographer Diogenes Laertius records Anaxagoras' doctrines, including the claim that the sun was a mass of fiery metal, in his Lives of the Philosophers. And the Roman naturalist Pliny the Elder, compiling the knowledge of the ancient world in his Natural History, recorded the Aegospotami stone as a famous instance of a body fallen from the sky. Across these independent sources, the same picture survives: a thinker who insisted the heavens were made of ordinary, if incandescent, matter, and a documented stone fall that seemed to bear him out. The closeness to the modern finding here is of a particular kind. The Egyptian and Andean traditions intuited that the precious metals belonged to the sky. Anaxagoras went further and asserted the deeper principle that makes tonight's whole study possible, that the sky and the earth are made of the same material, that there is no special heavenly substance separate from earthly stuff, and that matter can pass from the one to the other, falling as stone from above. This is, in its bones, the assumption behind every measurement in the modern record. When physicists look for supernova iron and R-process plutonium in a deep-sea crust, they are working from the premise that the matter of the stars and the matter of the earth are continuous, that atoms forged in the sky can come to rest in the ground, that a rock on the ocean floor can contain a piece of an exploded star. Anaxagoras said as much 25 centuries ago and was nearly destroyed for it. He had no instrument and no isotope. He had a stone that fell from the sky and the courage to follow it to its conclusion, that the heavens are not divine and separate, but material and connected, and that what is up there can come down here. The crust in the Pacific is the most patient confirmation his idea has ever received. We have held a number back through this entire report, and it is time to set it down, because only now, in the company of these four traditions, does it carry its full weight. Return to the missing isotope. The team searched the crust for curium-247, the faster decaying R-process partner of plutonium-244, and found none of it. From that absence, set against the surviving plutonium, they derived the date of the last major R-process event in the vicinity of our solar system. That date is at least 100 million years ago, more than 100 million years. Long enough that the curium has decayed away entirely, while only the longest-lived plutonium still lingers as a veil. To place that in a frame anyone can picture, the last time the space near us forged the heaviest matter in creation, the Earth was in the age of the dinosaurs. Flowering plants were young. The continents sat in different positions. No mammal larger than a small animal walked the planet. That is when the gold was last made nearby. Everything golden that has ever been mined, worn, hoarded, or buried by every human who has ever lived, is older than the oldest dinosaur fossil, by a wide margin, made in a catastrophe that predates almost everything we think of as ancient. That is the answer to the question planted at the start of this report. A missing isotope, curium-247, and the date its absence fixes, more than 100 million years, the deep time stamp on the last forging of the heaviest elements in our cosmic neighborhood. But there was a second question, the one we promised the four traditions would answer. How did peoples with no instruments arrive at a picture so close to this one? The traditions themselves show the method. The Egyptians reasoned from the behavior of gold, its refusal to decay, its solar color, and concluded it was a substance of the sky and the sun. The Inca reasoned from the same celestial association and named gold the sweat of the sun, a trace shed by a body in the heavens and settled into the earth. Anaxagoras reasoned from a fallen stone to the principle that the sky and the earth are one continuous material, and that matter falls from above. And the Burong did not reason at all in this case. They simply watched and recorded a great star convulsing in the night. 4 different methods on 4 different continents. Reasoning from permanence, reasoning from celestial likeness, reasoning from a fallen stone, and direct observation of the sky. 4 paths, and all of them arriving at the same country the isotopes now occupy. The conviction that the precious and the heaviest matter is of the sky, released by the sky, and only borrowed by the earth. They were not right in the way the instruments are right. They had no notion of a neutron star, no concept of rapid neutron capture, no way to date anything to 100 million years. The sun does not actually sweat gold. The true forge is rarer and older than the sun itself. But strip the religious and mythic language away and look at the structural claim underneath each tradition, and the same shape appears every time. The heaviest metals are celestial in origin. They come from events and bodies in the sky. They are deposited in the earth from above across great spans of time, and they are precious precisely because that celestial origin makes them rare. That is the claim the Egyptians, the Inca, Anaxagoras, and, in its own observational way, the Burong all reached. And it is allowing for the difference between myth and measurement, the claim a deep-sea crust and 3 accelerators confirmed this month. The convergence does not mean the ancients possessed secret knowledge. It means that the truth about where the heavy elements come from is, in its broad shape, available to anyone who watches the sky and the metals closely enough and is willing to follow what they observe to its conclusion. Across thousands of years and the whole spread of the inhabited earth, people did exactly that, and they pointed, again and again, upward. The crust in the Pacific held the record for more than 10 million years. The Egyptian texts held theirs for 5,000. The Andean tradition, the Greek philosophy, and the Burong star knowledge each held a piece of it across the centuries available to them. Tonight we have set the newest reading beside the oldest ones and found them facing the same direction. We have named the date and named the sources. What it adds up to, what it means that the gold in a wedding band was forged before the dinosaurs in the collision of dead stars and was called the flesh of the gods by people who could not have known it, is not ours to settle. The data is in the record. The interpretation belongs to you. Let us draw the night together slowly, because what was reported tonight rewards a careful closing as much as a careful opening. The starting point was a single object, a slab of ferromanganese crust from the floor of the Pacific Ocean, one of the most patient archives on the planet, grown so slowly that a few centimeters of it hold more than 10 million years of history in clean and unshuffled order. Into that crust, across the ages, fell the faintest dusting of matter from beyond the solar system, locked into the rock layer by layer at the depth corresponding to the moment it arrived. On the 15th of June, in the journal Nature Astronomy, an international team led from the Helmholtz Center in Dresden, working with accelerators in Canberra and in Sydney, reported what they had read out of that dust. 3 cosmic isotopes told the story, and the shape of each one mattered. Iron 60, the fingerprint of conventional supernovae, appeared in 2 distinct pulses, the chemical echoes of 2 stars that died near us within the last several million years, their debris washing over the Earth in broadened waves. Plutonium-244, forged only in the rare rapid neutron capture process, did not follow the iron at all. It lay across the record as a thin, even veil, the long-settled and well-mixed residue of something far older than the recent supernovae. And curium-247, the faster-decaying partner of the plutonium, the isotope that would serve as the clock, was searched for with the most sensitive instrument on Earth and was simply not there. From that absence, set against the surviving plutonium, the team fixed the last major event of heavy element forging in our cosmic neighborhood at more than 100 million years ago, in the age of the dinosaurs, in a catastrophe that was most likely the merger of two dead stars. Then we set that modern reading against the long human record and found that we were not the first to reach its central conclusion. The 30-year scientific climb from the first faint iron 60 inches a Munich laboratory in the late 1990s through the global map of nearby supernovae assembled in 2016 to the direct sighting of the cosmic forge in the neutron star merger of 2017 to the detection of plutonium that set up tonight's result is one record of how humanity learned that the heaviest matter is made in the sky. But beneath it lies an older record that reached a kindred conclusion without a single instrument. The Egyptians, who called gold the flesh of the gods and the substance of the sun, marked out by its permanence as a thing of the heavens. The Inca, who called gold the sweat of the sun and silver the tears of the moon, the trace shed by celestial bodies and settled into the earth. Anaxagoras, who argued from a fallen stone that the sky and the earth are one continuous material, and was charged with impiety for saying the sun was a stone rather than a god. And the Burong of southeastern Australia, who appear to have watched a great star convulse in the 19th century sky and fixed it in their knowledge as the large red star Calogoloric War, a record that modern cultural astronomy has matched to the eruption of Eta Carinae. 4 traditions, 4 methods, 1 destination. Reasoning from the permanence of gold, reasoning from its solar likeness, reasoning from a stone that fell, and watching the sky directly, peoples across the inhabited earth arrived, again and again, at the conviction that the heaviest and most precious matter is celestial in origin, released from the sky and only borrowed by the ground, and precious precisely because that origin makes it rare. The instruments have now confirmed the broad shape of that intuition and stamped a date on it. The gold in every ring and every hoard and every buried mask was forged before the dinosaurs, in the collision of dead stars, and has been thinning and settling through the local sky ever since. The ancients said it belonged to the heavens. The isotopes say they were, in the structural sense, correct. As this report is filed, the work is open and moving, and there are specific things worth watching in the hours, months, and years ahead. We will name them plainly, because this is a story that will be added to, not closed. The first thing to watch is the moon. The team has pointed to NASA lunar samples as the next archive in this investigation, material returned from the lunar surface that, lacking any atmosphere or ocean to filter and redistribute what falls on it, may hold an even cleaner ledger of the same cosmic isotopes than a deep-sea crust can. The question they intend to press there is the same one answered tonight, asked with finer resolution, the detailed history of the last R process event near us. Watch for measurements of iron, 6, 0, and eventually of the heavier R process isotopes in lunar material as a way of checking and sharpening the timeline read from the Pacific. The second thing to watch is an instrument. The team has noted that a new facility under development at the Helmholtz Center in Dresden, referred to as Hamster, is expected to reach a sensitivity comparable to the Vega Accelerator at the Australian Nuclear Science and Technology Organisation in Sydney, which is at present essentially the only machine on Earth able to detect these traces at the required level. When that German facility comes online, the detection of cosmic plutonium and curium and of other rare radionuclides will no longer rest on a single site. Tonight's kind of measurement will be repeatable and checkable in more than one laboratory, which is exactly how a young field hardens its results. The third thing to watch is the curium itself, now that it has a number attached to it. Tonight's search for cosmic curium 247 was the first significant attempt of its kind, and it returned an absence. That absence is informative, but the next stage is to push the sensitivity further still and to look in other archives to confirm that the curium really is gone everywhere it should be, and to tighten the date the team has placed at more than 100 million years. Watch for follow-up measurements on other crusts, and in lunar samples that test whether the figure holds and whether it can be made more precise. The fourth thing to watch is overhead, and it is continuous. The solar system is still moving through the local interstellar cloud, inside the larger local bubble, and the faint, well-mixed residue of that ancient R-process event is still settling onto the planet, even now, at a rate so low it took millions of years of crust to register it. We are inside the archive as it is still being written. Every deep-sea crust now growing on the Pacific floor is recording the present chapter of the same fall, and future researchers, reading those layers, will find the trace of the interstellar material the Earth is passing through tonight. The fifth thing to watch is the sky itself, through the gravitational wave observatories that caught the neutron star merger of 2017. As those detectors run and improve, they will register more such mergers, each one another direct sighting of the cosmic forge that made the plutonium in the crust. Every new detection adds to the count of observed R-process events and refines our sense of how often and how near such collisions occur, which feeds directly back into the question of when the last one happened close to us. The rock holds the local case. The detectors are building the universal census. The two will continue to inform one another. There is a sixth thing to watch, broader than any single instrument, and it is the widening of the question itself. The team has signaled that the new facility in Dresden is intended to detect not only plutonium and curium, but other rare radionuclides as well, isotopes that could open further windows onto how the elements form and how often nearby cosmic explosions have touched the solar system. Each such isotope is another hand on another clock, another way to date another kind of event in the deep past of our neighborhood. What began as a search for a single supernova fingerprint in one rock is becoming a systematic reading of the cosmic history written into the matter of the Earth. Watch, over the coming years, for the list of measurable cosmic isotopes to grow, and with it the resolution of the timeline they collectively record. The crust in the Pacific is one page. The field is learning to read the whole book. Hold all of this in the frame the ancient record gave us, because it is the frame that makes the watching worthwhile. We are, in the end, tracking the origin of the heaviest matter in the world and in ourselves, the gold and the platinum and the uranium, the trace metals woven through living cells. The instruments date its making to the deep past and locate its forge in the rarest catastrophe the universe stages. The old traditions, with no instruments at all, placed it in the sky and called it divine. Tonight, both the new record and the old one are open on the same desk, pointing the same direction. What remains is to keep reading, layer by layer, sample by sample, and to keep watching the sky that made us. It is worth ending on the quiet of it, because the loudest part of this story happened in silence, long ago and far away. Somewhere more than 100 million years ago, in the neighborhood of our young solar system, two dead stars finished a long fall toward one another and merged, and in a moment briefer than a heartbeat they forged a quantity of the heaviest matter that beggars description and flung it outward into the dark. There was no one to see it. The dinosaurs that walked the earth at the time would not have understood a flash in the sky as anything more than a light. And then the matter drifted and thinned and mixed into the slow currents of the interstellar medium, and across an unimaginable span of time, a vanishing trace of it found its way to a rock at the bottom of an ocean that did not yet exist when the event occurred. That is the chain tonight's report followed, backward, from a few atoms in a crust to a catastrophe older than almost anything we can name. And the people who came much later, who could measure none of this, looked at the gold the catastrophe had made, and somehow knew it did not belong to the earth. They called it the flesh of the sun, the sweat of a god, a stone fallen from a sky made of the same stuff as the ground. They were reading the only evidence they had, the strange permanence and the solar shine of the metal, and they followed it upward to the heavens, which is where it truly came from. There is a kind of continuity in that which is worth sitting with. The same sky that forged the gold was watched and reasoned about and recorded by people on 4 continents who never met, and tonight, with instruments those people could not have imagined, we confirmed the direction they were all pointing. The record is very old and very new at once, and it says the same thing in both registers. The heavy matter is of the sky. We are, in part, made of it. And the forge that made it has run, near us, only a handful of times in the whole long life of the world. That is the kind of report we file here every night. Tonight it was a deep-sea crust, 3 cosmic isotopes, and 4 ancient traditions that placed the origin of gold in the heavens long before anyone could prove it. What we add, beneath the event itself, is the layer most coverage leaves out, the long human record that watched the same sky, and the careful science that finally caught up to it. That layer is what would be missed by anyone who only read the headline and moved on. We file a new report at last light every night, because the data does not stop arriving and the record does not stop growing. If tonight was worth the hour, the comments are open. Tell us what stayed with you. Share this with someone who would sit with it too, and name the event we should take into the record next. And if this is work worth keeping close, here is the one quiet ask. Subscribe and stay with us. The file stays open. We will report again tomorrow.